Today I'm gonna read the book again. I think I'll read it only for 2 hours because I have a lot of stuff to do off stream. So let's start. Naming collisions and an introduction to namespaces. Let's say you're driving to a friend's house for the first time and your address given to you is 245 Front Street, Mill City. When reaching Mill City, you take out your map only to discover that Mill City actually has two different front streets across town from each other. Which one would you go to? Unless there were some additional clue to help you decide. Remember his house near the river. You have to call your friend and ask for more information. Because this would be confusing and inefficient, particularly for your mailman. Most countries, all street names and houses address with city required to be unique. Similarly, C++ requires all the identifiers be non-ambiguous. If two identical identifiers are introduced into the same program in a way that the compiler or linker can tell them apart, the compiler or linker will produce an error. This error is generally referred to as naming collision or naming conflict. So there's the same function named twice. It's gonna give a naming collision. The compiler compiles this program, it will compile CPP and main CPP independently, and each file will compile with no problems. Oh, sorry, two different files. However, when the linker executes, it will link all the definitions and it will have conflicting definitions. Most naming collisions occur in two cases. Two or more definitions for a function or a global variable are introduced into separate files that are compiled into the same program. This will result in a linker error, as shown above. Two or more definitions for a function or a global variable are introduced into the same file. Those result in a compiler error. The program gets larger and use more identifiers. The odds of a naming collision being introduced increases significantly. For its principle of mechanisms for avoiding name collisions, local scope keeps what is namespace. Back to our address analogy for a moment, having two front streets was only problematic because those streets existed within the same city. On the other hand, if you had to deliver mail to two addresses, one at 29 Front Street and another address at 417, there would be no confusion about where to go. Put another way, cities provide a grouping that allows us to disambiguate addresses that might otherwise conflict with each other. Namespaces act like the cities doing this analogy. Namespace is a region that allows you to declare names inside of it for the purpose of disambiguation. Namespace provides a scope called namespace scope to the names declared inside of it. Simply means that any name declared inside the namespace won't be mistaken for identical names in other scopes. Key insight: a name declared in the namespace won't be mistaken for an identical name declared in another scope. So pretty much what namespace does is maintain the integrity of the scopes. So it prevents but this leads to the question of if it's easier to make mistakes because then you can have functions that override other functions. In a namespace, all names must be unique, otherwise a naming collision will result. Namespaces are often used to group related identifiers in large projects to help ensure they don't inadvertently collide with other identifiers. For example, if you put all your math functions in a namespace called math, then your math functions won't collide with identically named functions outside the math namespace. Talk about how to create your own namespaces in the future lesson. The global namespace. In C++, any name that is not defined inside a class, function, or namespace is considered to be part of an implicitly defined namespace called the global namespace, sometimes also called the global scope. The example at the top of the lesson, function main, and both versions of my function are defined inside the global namespace. Naming collision encountered in the example happens because both versions of my function end up inside the global namespace, which violates the rule that all names in the namespace must be unique. Standard namespace. C++ was originally designed, all of the identifiers in the C++ standard library, including standard character in and character out, were available should be used without the standard prefix. They are part of the global namespace. However, this meant that any identifier in the standard library could potentially conflict with any name you picked for your own identifiers, also defining the globe's namespace. Code that was working might suddenly have a naming conflict when you included a new file from the standard library. Or worse, programs that would compile under one version of C++ might not compile under a future version of C++. As new identifiers introduced into the standard library could have naming conflict with already written code. So C++ moved all of the functionality in the standard library into a namespace named std, short for standard. So std is pretty much namespace. It turns out that standard count name isn't really standard count. It's actually just count. And standard is the name of the namespace that identifier count is part of, because count is defined in the standard namespace. Name count won't conflict with any objects or functions named count that we create in the global namespace. Similarly, when accessing an identifier that is defined in a namespace, you need to tell the compiler that we're looking for an identifier defined inside the namespace. Key insight. When you use an identifier that is defined inside a namespace, such as the std namespace, you have to tell the compiler that the identifier lives inside the namespace. There are a few different ways to do this. Explicit namespace qualifier std. Most straightforward way to tell the compiler that we want to use count from the standard namespace is by explicitly using their standard prefix. For example, when you say count, we mean that the count defined in the standard namespace. So this operator does that. This symbol is an operator called the scope resolution operator. The identifier to the left of the symbol identifies the namespace that the name to the right of the symbol is contained within. If no identifier to the left of the symbol is provided, the global namespace is assumed. So we say standard count, we're saying the count that lives in namespace standard. So it kind of directs the name to that thing. This is the safest way to use count because there is no ambiguity about which count we are referencing. The one in standard namespace. So I still have the question about this. Still have the question about how is this built on the C++ language itself. Best practice: use explicit namespace prefixes to access identifiers defined in the namespace. Using namespace standard and why to avoid it. Another way to access identifier is the namespace is choose a using directive statement. Here's our original hello world program with a using directive. So using namespace is using directive telling the compiler to check the standard namespace when resolving identifiers with no prefix. A using directive tells the compiler to check a specified namespace when trying to resolve an identifier that has no namespace prefix. In the above example, when the compiler goes to determine what identifier count is, it will check both locally where it is undefined and in the standard namespace where it will match no standard count. So let me read the part again. The compiler goes to determine whether identifier count, what identifier count is. It will check both locally where it is defined and in the standard namespace where it will match to. So the problem is that it gets the count from both. Oh, but here is the standard. Oh, so yeah, so it will check here and then in the standard library. Yeah, so when it tries to determine what count, it's gonna go through standard. Many text tutorials and even some compilers recommend or use a using directive at the top of the program. However, used in this way, this is a bad practice and highly discouraged. Consider the following program. Imports makes standard code accessible as count, declares function, count function, file error, which count we want, the function or the one that is a standard. The both program doesn't compile because the compiler now can't tell whether we want the count function that we defined or the count that is defined inside the standard namespace. And using directive in this manner, an identifier we define may conflict with any identically named identifier in the standard namespace. Even worse, while an identifier name may not conflict today, it may conflict with new identifiers added to the standard namespace in future language revisions. This was the whole point of moving all of the identifiers in the standard library into the standard namespace in the first place. By using directives, such as using namespace standard, that other program are in header files. They violate the reason why namespaces were added in the first place. Related content, we talk more about using statements and how to responsibly in lesson 6.12. So namespace is pretty much a way to access a library. So that's probably why classes use them as well. That two dots operator is just a way for C++ to tell to access the scope of the library, get from the scope. Introduction to the preprocessor. Translation preprocessor. When you compile your code, you might expect the compiler compiles the code exactly as you've written it. This actually isn't the case. Prior to compilation, the code file goes through a phase known as translation. Many things happen in the translation phase to get your code ready to be compiled. If you're curious, you can find a list of translation phrases here. A code file with translations applied to it is called a translation unit. The most noteworthy of the translation phases involves the preprocessor. The preprocessor is best thought of as a separate program that manipulates the text in each code files. The preprocessor runs, it scans through the code file from top to bottom looking for preprocessor directives. Preprocessor directives, often just called directives, are instructions that start with hashtag symbol and end with new line, not a semicolon. These directives tell the preprocessor to perform specific particular text manipulation tasks. Note that the preprocessor does not understand C++ syntax. Instead, the directives have their own syntax, which in some cases resembles C++ syntax and in other cases not so much. The output of the preprocessor goes through several more translation phases and then is compiled. Note that the preprocessor does not modify the original code files in any way. Rather, all text changes made by the preprocessor happens temporarily in memory each time code file is compiled. In the lesson we discussed what some of the most common preprocessor directives do. As an aside, using directives introduced in lesson 2.8 are not preprocessor directives, and those are not processed by the preprocessor. So while the term directive usually means a preprocessor directive, this is not always the case. Includes. We've already seen that the include directive in action. Generally, to include IOStream. When you include a file, the processor replaces the include directive with the contents of the included file. The included contents are then preprocessed along with the rest of the file and then compiled. When the program runs on when the preprocessor runs on the program, the preprocessor replaces include IOStream with the preprocessed contents of the file named IOStream. Since include is almost exclusively used to include header files, we will discuss include in more detail in the next lesson. Macro defines. The define directive can be used to create a macro. In C++, a macro is a rule that defines how input text is converted into a replacement output text. There are two basic types of macros: object-like macros and function-like macros. Function-like macros act like functions and serve a similar purpose. Do not discuss them here because their use is generally considered dangerous, and almost anything they can do can be done by a normal function. Object-like macros can be defined in one of two ways: define identifier, then substitution text. Top definition has no substitution text, whereas the bottom one does, because there are preprocessed directives, not statements. Note that neither from farm ends with a semicolon. Object-like macro with substitution text. When the preprocessor encounters this directive, any further occurrence of the identifier is replaced by substitution text. The identifier is traditionally typed in all capital letters, using underscores to represent spaces. Consider the following program. The process converts the above into the following. Contents of IO stream, so it's pretty much important. Define my name, Alex. So this allows it to create the reference to this thing here. The proof converts into the above, into the following. Which, when run, prints out the output. Object-like macros were used as a cheaper alternative to constant variables. Those times are long gone as compilers got smarter and the language grew. Object-like macros should only be seen in legacy code anymore. Recommend avoiding this kind of macros altogether, as there are better ways to do this kind of thing. We discussed this more in lesson cons XPA and symbolic constants. Object-like macros without substitution text. Object-like macros can also be defined without substitution text. Macros of this form work like you might expect. Any further occurrence of the identifier is removed and replaced by nothing. This might seem pretty useless and is useless for doing text substitution. However, that's not what this form of the directive is generally used for. Discuss the uses of this form in just a moment. Unlike the object-like macros with substitution text, macros of this form are generally considered acceptable to use. Conditional compilation. Conditional compilation preprocessor directives allow you to specify under what conditions something will or won't compile. There are quite a few different conditional compilation directives, but we will only cover the three that are used by far the most here: if def, if and def, and if. The if def preprocessor directive allows the preprocessor to check whether an identifier has been previously defined. If so, the code between the if def and matching and if is compiled. If not, the code is ignored. Consider the following program. So define, print show, if def, print show, and if. Print show is defined, compile this code. If def, print show, print ball, it's not gonna compile. Because print show has been defined, the line count show will be compiled. Because print bob has not been defined, it won't compile. If and defs is the opposite of if def, in that it allows you to check whether an identifier is not being defined yet. So if not defined, and if it's program prints bob because print bob was never defined. In place of if def and if def, you also see if defined and if not defined. This is the same, but it uses slightly more C++ style syntax. If zero. One more common use of conditional compilation involves if zero to exclude a block of code from being compiled, as if it were inside a comment block. What is the point of these things? This above code only prints Joe because Bob and Steve are inside an if zero block that the preprocessor will exclude from the compilation. It also provides a convenient way to comment out code that contains multi-line comments, which can't be commented out using another multi-line comment due to multi-lines comments being non-nestable. Also, this is useful to comment out code that is comment out inside. Objects like macros don't affect other preprocessor directives. Now it might be wondering. Since we define print show to be nothing, how come the preprocessor didn't replace print show in it if def print show with nothing? Macros only cause text substitution for normal code. Other preprocessor commands are ignored. Consequently, the print show in if def left alone. For example, so defines here if def not get replaced part of another preprocessor directive. In actuality, the output of the preprocessor contains no directives at all. They're all resolved to stripped out before compilation because the compiler wouldn't know what to do with them. Scope of defines. Directives are resolved before compilation from top to bottom on a file by file basis. Consider the following program. Define my name. Even though it looks like define my name as defined inside the function foo, processor won't notice, as it doesn't understand C++ concepts like functions. Therefore, this program that behaves identically to one where define my name Alice was defined either before or immediately after function foo. For general readability, you generally want to define identifiers outside of the functions. So for identifiers, you don't have scope. It doesn't matter if you put it inside or outside, it's going to be the same. Once the processor is finished, all defined identifiers from that file are discarded. This means that directives are only valid from the point of definition to the end of the file in which they are defined. Directives defined in one code file do not have impact on other codes. Files in the same project. Consider the following example. It will program opinions, even though print, yeah. Next one. Headers and their purpose. As programs grow larger and make use of more files, it becomes increasingly tedious to have to declare every function you want to use that is defined in a different file. Wouldn't it be nice if you could put all for declarations in one place and then import them when you need them? C++ code files with a CPP extension are not only files commonly seen in C++ programs. The other type of file is called a header file. Header files usually have a.h extensions, but you occasionally see them with a .hpp extension or no extension at all. The primary purpose of a header file is to propagate declarations to the code files. Key insight. Header files allow us to put declarations in one location, then import them wherever we need them. This can save a lot of typing in multi-file programs. I wonder why this is not done in other languages as well, where you just have all the imports on one file and you just import the file everywhere. I think one thing that might be different is that in C++ you don't specify the name of the file in order to call it. The functions that are inside of different libraries are just going to be imported. So this might be a problem of the execution because when it is linking is going to have conflicts of functions, which means a little bit more confusing. In Python, you can have the same function in different libraries, but because you have to call the library first in order to call the function from the library, there isn't this issue of conflicting functions. So that might be the case why it's different. This program prints hello world to the console using standard count. However, this program never provided a definition or regulation for standard count. So how does the compiler know what standard count is? The answer is that standard count has been for declared in the IOStream header file and include IOStream. We're requesting that the preprocessor copy all of the content, including for declarations for standard count from the file name IOStream to the file doing the include. Key insight: when you include a file, the content of the included file is inserted at the point of inclusion. This provides a useful way to pull in declarations from another file. Consider what would happen if the OStream header did not exist. Wherever you use standard count, you'll have to manually type or copy in all of the declarations related to standard count to the top of each file that uses standard count. This would require a lot of knowledge about how standard count was implemented and would be a ton of work. Even worse, if a function prototype changed, we'd have to go manually update our declaration. Yeah, so it's kind of redundant stuff. When it comes to functions and variables, it's worth keeping in mind that header files typically only contain function and variable declarations, not functions and variable definitions. Otherwise, a violation of the one definition rule could result. Standard count is for declared in the IOStream header, but defined as part of the C++ standard library, which is automatically linked into your program during the linking phase. So I have a feeling that this is not going to talk about the standard library. Include IO header file, compile make link, and runtime library. Best practice: header files should generally not contain function and variable definitions so as to not violate the one definition rule. An exception is made for symbolic constants, which you cover in lesson 4.15. Writing your own header files. Now let's go back to the example we were discussing in the previous lesson. On the left off, we had two files, add.cpp and main.cpp, that look like this. If you're recreating this example from scratch, don't forget to add.cpp to your project so it compiles. In this example, we use a for declaration so that the compiler will know what identifier add is when compiling main.cpp. As previously, so for declarations here. As previously mentioned, manually adding for declarations for every function you want to use that lives in another file can get tedious quickly. Let's write a header file to relieve us of this burden. So I already did this stuff on the course. I think we're just gonna not read everything. Use h suffix when running or naming your header files. Header files paired with a code file .h with add.cpp. You should both have the same base name. Add. Here's our completed header file. We should have a header guard here, but we will omit it for simplicity. So I guess this is you can have multiple header files, and each one of them is gonna work as a library for definitions. So I guess that's the difference on Python of using the render method in the end to determine. So usually people say to do like this when you wanna build a script and when you wanna build something that is not supposed to be run, like a library, you don't type this at the end. And I think this might be the case because files that don't have this are better compiled as header files, and when you have these, then they're considered to be scripts. I'm not really sure. This is the content of the H file, which is where the declaration goes. Function prototypes, don't forget semicolon. In order to use this header file in main.cpp, you have to include using quotes, not angle brackets. If your processor processes the include add htd line, it copies the contents of add.h to the current file at that point, because our add.h contains a for declaration for function add. The for declaration will be copied into main.cpp and results a program that is functionally the same as the one where we manually added the for declaration at the top of main.cpp. Consequently, our program will compile and link correctly. So add main include hg compile add o then links main compiles and links include iostream header file compiles links. So compiles everything and then links them. Source files should include their paired header. In C++, it is a best practice for code files should include their paired header file if one exists. The example above add.cpp includes add.h. This allows the compiler to catch certain kind of errors at compile time instead of link time. Return type for declaration. Error wrong return type. So you can't call using void. Can't call using int because it was declared as void. I think. Because something.cpp includes something.h, the compiler will notice that function something has a mismatched return type and give us a compiler error. If something.cpp do not include something.h, we'd have to wait until the linker discovers the discrepancy, which wastes time. For another example, see this comment. Source files should include their paired header file, if one exists. Troubleshooting. If you get a compiler error indicating that add.h isn't found, make sure the file is really named add.h. Depending on how you created and named it, it's possible the file could have been named something like add an extension or add.h.text or add.hpp. Also make sure it's sitting in the same directory as the rest of your code files. If you got a link error about function add not being defined, make sure you've added add.cpp in your project so the definition for function add can be linked into the program. Angle brackets versus double quotes. You're probably curious why we use angle brackets for iostream and double quotes for add.h. It's possible that a header file with the same file name might exist in multiple directories. Our use of angled brackets versus double quote helps give the compiler a clue as to where it should look for header files. When you use angle brackets, we're telling the processor that this is a header file we didn't write ourselves. The compiler will search for the header only in the directories specified by the include directories. The include directories are configured as part of your project ID setting, compiler setting, and typically default to the directories containing the header files that come with your compiler and our OS. The compiler will not search for the header file in your project's source code directory. When we use double quotes, we're telling the preprocessor that this is a header file that we wrote. The compiler will first search for the header file in the current directory. If it can't find a matching header there, it will then search the include directories. So the angle brackets is for files of the system, and the other is for the files built. Rule: use double quotes to include other files that you've written or expected to be found in the current directory. Use angle brackets to include headers that come with your compiler. OS or third-party libraries you've installed elsewhere on your system. Why doesn't IO have a .h extension? Another commonly asked question is why doesn't iostream or any of the other standard library header files have a .h extension? The answer is that iostream.h is a different header file than iostream. To explain requires a short history lesson. In C++, was first created, all the files in the standard runtime library ended in a .h suffix. Life was consistent and it was good. The original version of count and sing were declared in iostream.h. When the language was standardized by the NC committee, they decided to move all of the functionality in the standard library into the std namespace to help avoiding naming conflicts with user-defined identifiers. However, this presented a problem. If they moved all the functionality into the standard namespace, none of the old programs that include the iostream.h would work anymore. To work around this issue, a new set of header files was introduced that use the same name but lack the h extension. These new header files have all their functionality inside the standard namespace. This way, older programs that include iostream do not need to be rewritten, and newer programs can include iostream. In addition, many of the libraries inherited from C that are still useful in C++ were given a C prefix. Standard library.h became cstdlib. Functionality from these libraries was also moved into the standard namespace to help avoid naming collisions. Best practice when including a header file from the standard library is the version without the .h extension if it exists. User-defined headers should still use a .h extension. So another question that popped up in my mind is that why int, boolean, and all the other methods don't have a std before them if they come from the iostream library, because they seem to be they they definitely are methods from the C++ language. So why they are not included in the library, or why do don't why it isn't needed to specify where they're coming from by using the namespace. Another common question involves how to include header files from other directories. One better way to do this is to include a relative path to the header file you want to include as part of the include line. For example, while this will compile assembly files existing in those relative directories, the downside of this approach is that it requires you to reflect your directory structure in your code. If you ever update your directory structure, your code won't work anymore. A better method is to tell your compiler or IDE that you have a bunch of header files in some other location, so that it will look there when you can't find them in the current directory. This can generally be done by setting an include path for search directory in your IDE project setting. For Visual Studio users, right-click on your project in the Solution Explorer and choose Properties, then VC++ Directories tab. From here, you see a line called Include Directories. Add the directories you like the compiler to search for additional headers there. I think I'm gonna print this because it is important. It's very useful. And I'm definitely gonna forget about this later on. Nice thing about this approach is that if you ever change your directory structure, you only have to change a single compiler or the setting instead of every code file. Header may include other headers. It's common that a header file will need a declaration or definition that lives in a different header file. Because of this, header files will often include other header files. When your code file includes the first header file, you also get any other header files that the first header includes. These additional header files are sometimes called transitive includes, as they're included implicitly rather than explicitly. The content of these transitive includes are available for use in your code file. However, you should not rely on the content of headers that are included transitively. Implementation of header files may change over time or be different across different systems. If that happens, your code may only compile on certain systems or may compile now but not in the future. This is easily avoided by explicitly including all of the header files the content of your code file requires. Best practice, each file should explicitly include all of the header files it needs to compile. Rely on headers included transitively from other headers. Unfortunately, there is no easy way to detect when your code files accidentally rely on content of a header file that has been included by another header file. I did include some header and my program worked anyway. Why? This is one of the most commonly asked questions on the site. The answer is it's likely working because you included some other header, which itself included some header. Although your program will compile where the best practice above, you should not rely on this. What compiles for you might not compile on a friend's machine. So the thing, I think what they're saying is if you include a header that is already included inside of another header, outside of the header, it is not going to give you a problem. It's just going to get the statement from the header instead of the transitive header that lives inside of the other header. If that makes sense. The include order of header files. If your header files are written properly and include everything they need, the order of inclusion shouldn't matter. Now consider the following scenario. Let's say header A needs declaration of header B, but forgets to include it. In our code file, if we include header B before header A, our code will still compile. This is because the compiler will compile all the declarations from B before it compiles code from A that depends on those declarations. However, if we include header A first, then the compiler will complain because the code from A will be compiled before. It is actually preferable because the error has been surfaced and we can then fix it. To maximize the chance that missing includes will be flagged by compiler, order your includes as follow. The paired header file, other header from your projects, third-party library headers, standard library headers. The headers for each group should be sorted out alphabetically. That way, if one of your user-defined headers is missing and include for a third-party library or standard library header, more likely to cause a compiler error so we can fix it. So you assign the made-up headers first. Header file best practices. So the first one is obviously IO stream, then there are headers, then third-party headers. Third-party headers. Header file best practice. Here are a few more recommendations for creating and using header files. Always include header guards. We'll cover this next lesson. Do not define the variables and functions in header files. Global constants are an exception. We'll cover this later. Give your header files the same name as the source files they're associated with. Each header file should have a specific job and be as independent as possible. For example, you might put all your declarations related to the functionality A in A.h and all your declarations related to a functionality B in B.h. That way, if you only care about A later, you can just include A and not get any stuff from B. Be mindful of which headers you need to explicitly include for the functionality that you are using in your code files. Every header you write should compile on its own. Should include every dependency it needs. Only include what you need, don't include everything just because you can. Do not include CPP file. Header guards, the duplicate definition problem. In lesson 2.6, noted that a variable or function in the identifier can only have one definition. Thus, a program that defines a variable identifier more than once will cause a compile error. Similarly, programs that define a function more than once will also cause a compile error. While these programs are easy to fix. So I didn't know this. No, you can compile. You can declare twice. Same. Yeah, you can reassign the value, but you can declare twice. I guess that makes sense. While these programs are easy to fix, remove the duplicate definition for header files. It's quite easy to end up in a situation where the definitions in a header file gets included more than once. This can happen when a header file includes another header file, which is common. Consider the following academic example. Yeah, so you get lost because there's too many functions and too many files. This silly innocent looking program would compile is what's happening. I guess let's skip this. Header guards. The good news is that we can avoid the above problem via mechanism called a header guard, also called an include guard. Header guards are conditional completion directives that take the following form. Declarations and certain types of definitions here, and so that's why this stuff is used. When the header is included, the preprocessor checks whether some unique name here has been previously defined. If this is the first time we're including the header, some unique name here will not have been defined. Consequently, it defines some unique name here, then includes the contents of the file. If the header is included again into the same file, some unique name will already have been defined from the first time the contents of the header were included, and the contents of the header will be ignored. Then true if and if. All of your header files should have header guards on them. Some unique name here can be any name you want, but by convention is set to the full file name of the header file. And typed in all caps, using underscore for spaces or punctuation. For example, square.h would have the header guard square.h in caps lock. If def, define def. So if it's not, doesn't exist, then you define it. Even in the standard library, headers use header guards. If you first take a look at the IOStream header file from Visual Studio, you would see. For advanced readers, in large programs, it's possible to have two separate header files, included from different directories, that end up having the same file name. G directory A config H and directory B config H. If only the file name is used for the include guard, these two files may end up using the same guard name. If that happens, any file that includes directly or indirectly both config.h files will not receive the contents of the include file to be included second. This will probably cause a compilation error. Because of this possibility for guard name conflicts, many developers recommend using a more complex unique name in your header guards. Some good suggestions are name convention of project path, file, age, file, large random number, age or file, creation date, age. Updating our previous example with header guards. Let's return to the square example. For good form, we also add header guards to geometry.h. So it includes in the main and puts the statements on the header files. After the preprocessor resolves all the includes, this program looks like this. Square age included from mains B. Geometry age included from mains B. Square age included from geometry.h. Square age is already defined from above. So it gets this one. And it skips this one because it's already defined. As you can see from the example, the second inclusion of the contents of square age from geometry age gets ignored because square age was already defined from the first inclusion. Therefore, our function gets square sides only gets included once. Header guards do not prevent the header from being included once into different code files. Note that the goal of header guards is to prevent a code file from receiving more than one copy of a guard header. By design, header guards not prevent a given header file from being included once into separate code files. This can also cause unexpected problems. Consider age, square age, or declaration for square perimeter. Square CPP is included once here. And here has a function. Yeah, this gets pretty confusing. It's also included here. So it's included in both files. Note that square age included from both main and square CPP. This means the contents of square.age will be included once into square.cpp and once into main. Let's examine why this happens in more detail. When square.age is included from square CPP, square age is defined until the end of square CPP. This define prevents square.age from being included to square CPP a second time, which is the point of header guards. However, once square CPP is finished, square age is no longer considered defined. This means that when the preprocessor runs on main CPP, square age is not initially defined in main CPP. The end result is that both square.cpp and main.cpp get a copy of the definition of get square sides. This program will compile, but the linker will complain about your program having multiple definitions for identifier get square sides. Best way to work around this issue is simply to put the function definition in one of the CPP files to the header, so that the header just contains a for declaration. So for declaration on the same file for both functions. Yeah, I'm not sure if I completely follow this. It's probably important as well. I think, yeah, it is really important and is one of the most difficult things about programming. It's understanding this scope of things. But it's very confusing. So it includes this file that has these definitions, which is the header. Yeah, this is the definition, this is the header. Square age is also included here. So it's including the definition from both, for both. Now when the program is compiled, function get square sides will have just one definition. Be square CPP, so the linker is sampling. File main CPP is able to call this function, even though it lives in square CPP, because it includes square.age, which has a for declaration for the function. So this code is able to call this function that lives in here, because the declaration is on the header file, and this code includes the header file. I think I get it now. Which has a for declaration for the function. The linker will connect the call to get square sides. From main.cpp, definition of get square sides in square cpp. Can't we just avoid definitions in header files? We've generally told you not to include the function definitions in your headers. So maybe you wonder why you should include header guards if they protect you from something you shouldn't do. There are quite a few cases we will show you in the future where it's necessary to put non-function definitions in a header file. For example, C++ will let you create your own types, These user-defined types are typically defined in header files, so the type definition can be propagated out to the code files that need to use them. Without a header guard, a code file could end up with multiple identical copies of a given type definition, which the compiler will flag as an error. So even though it's not strictly necessary to have header guards at this point in the tutorial series, we're establishing good habits now, so we don't have to unlearn bad habits later. Pragma once. Many compilers support a simpler alternative from form of header guards using Pragma directive. Pragma once serves the same purpose as header guards and has the added benefit of being shorted and less error prone. However, Pragma once is not an official part of the C++ language, and not all compilers support it, although most modern compilers do. For comportability purposes, we recommend sticking to traditional header guards. They aren't much more work, and they are guaranteed to be supported on all compliant compilers. Summary: header guards are designed to ensure that the contents of a given header file are not copied more than once into any single file. In order to prevent duplicate definitions, note that duplicate declarations are fine, since the declaration can be declared multiple times without incident. But even if your header file is composed of all declarations, no definitions, it is still best practice to include header guards. Note that the header guard do not prevent the contents of a header file from being copied once into separate project files. This is a good thing because we often need to reference the contents of a given header from different project files. How to design your first programs. Now that you've learned some basics about programs, let's look more closely at how to design a program. When you sit down to write a program, generally you have some kind of idea which you'd like to write a program for. New programmers often have trouble figuring out how to convert that idea into actual code, but it turns out that we have many of the problem-solving skills you need already acquired from everyday life. Most important thing to remember and hardest thing to do is to design a program before you start coding. In many regards, programming is like architecture. What would happen if you tried to build a house without following an architectural plan? Odds are, unless you were very talented, you'd end up with a house that had a lot of problems. Walls that weren't straight, a leaky roof, etc. Similarly, if you try to program before you have a good game plan moving forward, you will likely find that your code has a lot of problems, and you have to spend a lot of time fixing problems that could have been avoided altogether with a little thinking ahead. Little from planning will save you both time and frustration in the long run. In this lesson, we'll lay out a generalized approach for converting ideas into simple functional programs. So far, there's a lot of stuff in my mind already from the previous stuff. Design step 1. Define your goal. In order to write a successful program, you first need to define what your goal is. Ideally, you should be able to state this in a sentence or two. It's often useful to express this as a user-facing outcome. For example, allow the user to organize a list of names and associated phone numbers, generate randomized dungeons that will produce interesting-looking caverns, generate a list of stock recommendations for stock that have high dividends, model how long it it takes for a ball dropped off a tower to hit the ground. Although this step seems obvious, it's also highly important. The worst thing you can do is write a program that doesn't actually do what you or your boss wanted. Design step 2. Define requirements. While defining your problem helps you determine what outcome you want, it's still vague. The next step is to think about requirements. Requirements is a fancy word for both the constraints that your solution needs to abide by. Budget, timeline, space, memory, etc. As well as the capabilities that the program must exhibit in order to meet the user's needs. Note that your requirement should similarly be focused on the what, not the how. For example, phone numbers should be saved so they can be recalled later. The randomized dungeon should always contain a way to get from the entrance to an exit. Stock recommendations should leverage historical pricing data. The user should be able to enter the height of the tower. In a testable version within 7 days, the program should produce results within 10 seconds of the user submitting the request. The program should crash in less than 0.1% of the user session. Single problem may yield many requirements and the solution isn't done until it satisfies all of them. Define your goals, your tools, targets, and backup plan. When you're an experienced programmer, there are many other steps that typically would take place at this point, including defining what target architecture or OS your program will run, determine what set of tools you'll be using, determine whether you write your program alone or as a part of a team, define your testing feedback release strategy, determine how you back up your code. However, as a new programmer, the answer to these questions are typically simple. You're writing a program for your own use, alone on your own system, using an IDE you purchased or downloaded, and your code is probably not used by anybody but you. This makes things easy. That said, if you're going to work on anything of non-trivial complexity, you should have a plan to back up your code. It's not enough to just zip or copy the directory to another location on your machine, so this is better than nothing. If your system crashes, you lose everything. A good backup strategy involves getting a copy of the code off your system altogether. There are lots of easy ways to do this. Zip it up and email it to yourself, copy it to a Dropbox, or another cloud service FTP to another machine, copy it to another machine on your local. That's pretty much just uh, obvious stuff. Break hard problems down into easy problems. I don't think I'm gonna read this stuff. Just very redundant, basic stuff. Figure out the sequence of events. Implementation step 1, outline your main function. I think now is the coding part. Now we're ready to start implementation. The above sequences can be used to outline your main program. Don't worry about the inputs and outputs for the time being. Or in the case of the calculator. Note that if you're going to use this outline method for constructing your program, your functions don't compile because the definitions don't exist yet. Commenting out the function calls until you're ready to implement the function definition is one way to address this. The way you show here. Implementation function, testing, words of advice when writing programs. Your program simpler to start, add features over time, focus on one error at a time, test each piece of code as you go. Don't invest in perfecting your code. Function, definition. When two identifiers are introduced into the same program in a way that the compiler or linker can tell them apart, the compiler or linker will produce a naming collision. Namespace guarantees that all identifiers within the namespace are unique. Standard namespace is one such namespace. The preprocessor is a process that runs on the code before it is compiled. Directives are special instructions to the preprocessor. Directives start with a hashtag symbol and end with a new line. A macro is a rule that defines how input text is converted to a replacement output text. Header files are files designed to propagate declarations to code files. Using the include directive is replaced by the contents of the included file. When including headers, use angle brackets when using system headers and double quotes are user defined. Include the version with no HP. Header guards prevent the contents of a header from being included more than once into a given code file. They do not prevent the contents of a header from being included into multiple different code files. Quiz time. Be sure to use your editor's auto formatting feature to keep your formatting consistent and make your code easier to read. Write a single file program in namespace that reads two separate integers from the user. I'm not gonna do this stuff. I think it would be good to take a look at some code from more experienced people to see what's usually happening. So I have some context to know how these things are used in practice usually. Syntax and semantic errors. Structural errors are prevalent, it's easy to make them, and it's hard to find them. This chapter will explore topics related to the finding and removal of bugs within our C++ program, including how to use the integrated debugger that is part of our IDE. Although debugging tools and techniques are part of the C++ standard, learning to find and remove bugs in the program you write is an extremely important part of being a successful programmer. Therefore, we spend a bit of time covering such topics so that as the programs you write become more complex, your ability to diagnose and remedy issues advances at a similar pace. Syntax and semantic errors. Programming can be challenging, and C++ is somewhat of a quirky language. Put those two together, and there are a lot of ways to make mistakes. The errors generally fall into one of two categories: syntax errors and semantic errors. Syntax error occurs. I think it's gonna be talk about the basic stuff probably. Semantic error occurs when a statement is syntactically valid, but that's not what the program is intended. Modern compiles have been getting better at this detecting a certain type of common. Not gonna read this stuff. General approach to debugging. Find the root cause of the problem, ensure you understand why the issue is occurring. Determine how you fix the issue. Repair the issue causing the problem. So a lot of this is just common sense. Finding problems via code inspection. Let's say you've noticed a problem and you want to track the cause of the specific problems down. In many cases, especially in smaller programs, we can quickly home in on the proximity of where the issue is. Finding problems by running the program. So I wonder if they're gonna talk about actual tools about IDEs and how to use them. If you can't find an issue via code inspection, there's another avenue we can take. We can watch the behavior of the program as it runs and try to diagnose the issue from that. This approach can be generalized as figuring out how to reproduce a problem, run the program, and gather information to narrow down where the problem is. Repeat the prior step until you find the problem. Reproducing the problem, on the issue, blah blah blah. Commenting out your code, debugging tactic 2, validating your code flow. When printing information for debugging purposes, use standard C instead of standard count. One reason for this is that standard count may be buffered, which means there may be a pause between when you ask standard count to output information and when it actually does. If you output using standard count and then your program crashes immediately afterwards, standard count may or may not have actually output yet. This can mislead you about where the issue is. the other hand, standard sir is unbuffered, which means anything you send to it will output immediately. This helps ensure all the debug output appears as soon as possible, at the cost of some performance, which we usually don't care about when debugging. So this is a useful tip to know. Useful thing to know. Using standard sir character error, assume that's what it stands for. Also helps make clear that the information being output is for an error case rather than a normal case. Consider the following program that doesn't work correctly. You may need to disable the treat warnings as errors for the above to compile. Although we expect this program to print the value of 4, it will actually print different values on different machines. On the author's machine, it printed this. So it's because of the scope of the variable. Let's add some debugging statements to these functions. Yeah, so it's adding the print to both. When adding temporary debug statements, it can be helpful to not indent them. This makes them easier to find for removal later. Now, when these functions execute, they output their names, indicating that they were called. Now you can see the function getValue was never called. There must be some problem with the code that calls the function. Oh, so it's not calling the function. That's the problem. Let's take a closer look at that line. Or look with red parentheses on the function. This will now produce the correct output. So I was wrong. I thought it was because of the scope of the variable. And we can remove the temporary debugging statements. Debugging tactic, printing values. With some types of bugs, the program may be calculating or passing the wrong value. You can also output the value of variables, including parameters or expressions, to ensure that they are correct. Consider the following program that is supposed to add two numbers but doesn't work correctly. Here's some output from this program. That's not right. Do you see the error? Even in this short program, it can be hard to spot. Let's add some code to debug our values. Yeah, I don't feel like reading or paying too much attention to this stuff because I'm trying to only get to the parts that I think are interesting now. And I'll probably review these concepts later anyway, when I'm actually coding. The variable z isn't variable I that value 3, but somehow the function I got the value of 5. Values in pretty to the debug isn't great. While adding debug statements to programs for diagnostic purposes is a common rudimentary technique and a functional one, especially when the debugger is not available for some reason. It's not great for a number of reasons. Debug statements clutter your code, clutter the output of your program, must be removed after we're done, which makes them not reusable. Require modification of your code to both add and to remove, which can introduce new bugs. Also, they talk about how in the future lessons. That's the annoying thing about books. This, not all books, but these kinds of books, there is a lot of stuff that is kind of just to fill in pages to make the thing seem that is worth more than it is. And a lot of books do that. first one that comes to mind is The One Thing, I think. It's pretty much a book based on only one simple idea. But they have to put a bunch of pages so it sells more. Because people equate pages with value. So I don't know. I'm having second thoughts about reading this whole thing. Hey man, I think it might be more efficient to research what I'm thinking about. Let me see the chapters of the book. Yeah, we can jump to the ones that I think that might have something that I don't know. Or that I'm curious about now. So I think I'm here. No. Already I'm already here. Wow, I read a lot of stuff. Yeah, header files, header guards, debugging, I'm here. Strategy for debugging. I'm from Brazil. But yeah, Portuguese is the same, is the language. I think I might read it like this instead of reading every single page. So I think I'm on the debugging tactics. Yeah, this one is where it starts to get interesting. Definitely curious about this operators, bit manipulation. Yeah, this is very interesting. Bitwise operators, which was the stuff that the other guy was talking about the other day. Manipulation of bitwise operators and bitmasks, converting bit between binary and decimal. Scope, duration, and linkage. Yeah, so the rest seems interesting. I think it was just because I was in the very beginning, so it seems very uh, basic, let's say. Not sure if that's the right word. Chapter 8 is newly added. So maybe, yeah, I think maybe what I would do is instead of reading for 2 hours each day, I'm gonna read for 1 hour. Next time I do this, I'm gonna read for 1 hour and then I'm gonna watch videos about the chapter I just read. The not the chapter, but the pages I just read. I read it next. It's very exhausting to read, and the concentration decreases rapidly. It's very intensive. Yeah, so there's a bunch of stuff. I kind of want to look at videos to see people coding stuff. To see the actual code that in practice, the best practice and what people usually do. So I know what to pay attention more when I'm reading this. And I think I'm gonna move the stuff that I have from the other browser to this one. The playlists. So I watch them on this browser instead. More debugging tactics. In the previous lesson, we started exploring how to manually debug problems. That lesson we offered some criticism of using statements to print debug text. Debug statements, clutter. So we can mitigate some of these issues in this lesson. We'll explore some basic techniques for doing so. Conditionalizing your debugging code. Consider the following program that contains some debug statements. So this one. When you're done with the debugging statements, we either need to remove them or comment them out. Then if you want them again later, you have to add them back or uncomment them. One way to make it easier to disable and enable debugging throughout your program is to make your debugging statements conditional using preprocessor directives. Comment out to disable debugging. So declare at the top, and then when you want to disable these debugs, you just comment this line, and all of them are disabled. Now we can enable debugging by simply by commenting on commenting define and enable debug. This allows us to use previously added debug statements and then just disable them when we're done with them, rather than having to actually remove them from the code. If this were a multi-file program, the define enable debug would go in a header file that's included into all code files, so we can comment the comment to the define in a single location and have it propagate to all code files. This addresses the issue of having to remove debug statements and the risk in doing so, but at the cost of even more code clutter. Another downside of this approach is that if you make a typo, misspell debug, or forget to include the header into a code file, some or all of the debugging for the file may not be enabled. So though this is better than the unconditionalized version, there is still room to improve. Using a logger, an alternative approach to conditionalized debugging via the preprocessors to send your debugging information to a log file. A log file is a file normally stored on disk that records events that occur in software. The process of writing information to a log file is called logging. Most applications and operating systems write log files that can be used to help diagnose issues that occur. Log files have a few advantages. Because the information written to a log file is separated from your program's output, you can avoid the clutter caused by mingling your normal output and debug output. Log files can also be easily sent to other people for diagnosis. So if someone using your software has an issue, you can ask them to send you the log file. And it might help give you a clue where the issue is. While you can write your own code to create log file and send output to them, you're better off using one of the many existing third-party logging tools available. Which one you use is up to you. For illustrative purposes, we'll show what outputting to a logger looks like using the plug logger. Plug is implemented as a set of header files, so it's easy to include anywhere you need it, and it's lightweight and easy to use. So include the headers. Is defined by the plug library. So just use this name here. Initialize the logger. I'm not sure if I'm gonna remember all of this. Probably not. I'm honest. Output to the log as if you were writing to the console. Here's output from the above logger. Called, get it, called. How you include, initialize, and use a logger will vary depending on the specific logger you select. Note that conditional compilation directives are also not required using this method, as most loggers have a method to reduce, eliminate writing output to the log. This makes the code a lot easier to read, as the conditional compilation lines add a lot of clutter. With blog, logging can be temporarily disabled by changing the init statement to the following. So just change to none here. Eliminates writing of most messages, essentially turning logging off. So it just removes the clutter from the output, but the code itself is still clutter. We won't use plug in any future lessons, so you don't need to worry about learning it. As an aside, if you want to compile the above example yourself or use plug in your own projects, you can follow these instructions to install it. List plug release, click the green code, next unzip entire archive somewhere on your hard drive. Finally, for each project, set the somewhere plug master include directory as an include directory inside your ID. There are instructions on how to do this for Visual Studio and code blocks. Using an integrated debugger, stepping. I think I'm gonna go to the bathroom. I think I might need read some parts in silence as well because that might be one of the reasons why I'm getting tired faster. So there are about 17 chapters, but some of them are bigger than others. 15. This is 12. So I think this one, and up to here, I think. Oh, up to 2.8 took me 6 hours to read. So let's do some math. If every one of them takes me about every chapter takes me about 4 hours, gonna be 17, 68 hours divided by 2, 34. This is gonna take me 68 days to read this, the whole thing. 32 hours a day. 34 days. 32 hours a day. So I think I'm gonna just read silently so so it's easier. Maybe I'll put some music in the background. Just gonna put it very low volume. Yeah, I think the best strategy is gonna be to just read, I think, for half an hour out loud in the beginning, and then read the rest of the time silently, listening to some music. Otherwise, I'm not gonna last very long, I think. And I want to increase the amount of time I spend reading, so I finish the book faster. So this is very useful to know. So it executes the code line by line. So step over executes the whole thing. Step executes one by one. And step over. Step in through, step over. So F11, F down, run and shift F down for the step out. One question that this brings to my mind is what happens if you stop the execution in the middle of the main function? It's gonna give you an error because it doesn't have a return, but then will you will it let you figure out what's the problem? I know this is important stuff, or one of the most important things debugging, but it's really boring for me, especially when I don't have experience yet, because it's hard to see, to envision the how practical, how much it's gonna, how how much time is gonna save me when I'm coding. Let me see how many of these questions I still have. String manipulation. So this operator is namespace. I think I can erase this. I'm not sure if I'm gonna study the library itself. I'll think about it after I finish the book. I'm gonna read this last page and then I'll stop. Let me write that down. I could have written all of them in a notebook for remembering faster. The ones that I think that are important. I'll leave them here for now. Got this one. So I think I'm gonna stop here. I'm quite tired, to be honest, and I might come back even today to read more. I wanna finish this as fast as possible, ideally, and yeah, let's see here. But I have a bunch of stuff to do outside of the stream as well. So hopefully I'll be able to finish what I have to do outside of the stream fast, and then once I get to that point, I can spend more time reading. So yeah. So I'll either come back today or probably tomorrow to continue reading this. So see you.